Hello, this is Gary Millett. This is the last topic number 5 in the wireless networking course, and it's about basic antenna theory. So it's a very short version of antenna theory, which is a very complicated topic, but nevertheless, we'll try to simplify it for people to grasp the basic concepts. So let's get started. So for any wireless system, an extremely critical component is the antenna. This is the part that interfaces the transmitter electrical signal to the air or free space, where the signal now exists as an electromagnetic wave. So let's do a definition of the antenna. So an antenna is a physical device / structure that converts electrical energy propagating on a transmission line into electromagnetic energy propagating into free space, or vice versa. So it's a reciprocal process. The first case is called transmission, where we launch an electromagnetic wave, while the second case is called reception, where we intercept an electromagnetic wave and cause a signal to propagate back down a transmission line. So basic antenna is what we'll look at next. Antenna theory is based heavily on models, since the mathematics to deal with them is inherently difficult and problematic. So let's start with the idea of a point source. This model is familiar through our life experiences of seeing our solar system sun or viewing stars in the sky at night. The point source radiates equally in all directions. Another way of expressing this concept is that a point source has no favored direction of radiation. We would call that omnidirectional. For the earliest wireless applications, those were low-frequency broadcasting, the most important task of an antenna was to efficiently convert the transmitted signal into an electromagnetic wave. The next most important antenna task was to provide an omnidirectional signal to reach the most potential listeners, assuming that they were spread out equally around wherever the antenna was. As time passed and the frequencies used for wireless increased, the first task became easier to achieve, and the second task may or may not be as important, depending upon the wireless service being implemented. If I want a point-to-point link, I don't need an omnidirectional antenna anymore. So if one ran a shortwave radio station and wanted to reach a certain distant area, one might want to fashion an antenna that did favor a particular direction over all others. So making an antenna directional so as to squint the radiated signal in a particular direction became the goal of the antenna design engineer. That brings us to the basic fundamental antenna known as the half-wave dipole. So here's a picture of a half-wave dipole, and notice that its length is 1/2 wavelength, and you might think that that would just be using the wavelength equation. You actually have to take into account the diameter or size of the elements that make up the half-wave dipole. If it's wire tends to be infinitely thin, and you can use the regular wavelength equation. So the basic half-wave dipole wire antenna shown here is a practical antenna. It may be realized for most frequencies and is used extensively as a basic antenna building block for array antennas. It has a donut-shaped radiation pattern, which I'll show you on the next slide. Notice the feed line goes to the two elements that make up the half wavelength portion of the antenna. So here's this nice colorized version, radiation pattern of a half wavelength dipole by antennatutorials.com. And if you go to that website, you will probably find more antennas and their wave patterns, radiation patterns. So in this graphic, the half-wave dipole antenna would be located at the center of this radiation pattern, and it'd be oriented vertically. So just think of the antenna in the prior slide as being flipped on 90 degrees, and it's put down into the hole of the donut there. What this means is that no energy is radiated off the ends of the antenna, but instead it is mostly radiated perpendicular to the antenna. You could do a search of YouTube videos to find animations of various antenna radiation patterns, or maybe go to antennatutorials.com. Now, there are many different types of antennas, so there are many different types of practical antennas that take on numerous geometric shapes. However, there is one universal constant for any type of antenna. For efficient radiation, an antenna's size must be approximately 1/2 wavelength or greater. We have not been able to overcome this limitation. Some people have talked about making antennas out of coils of wire, like inductors, and it turns out that nothing practical has ever come of that. Some of the more popular antenna types or categories are wire, aperture, reflector, microstrip patch, lens, and array antennas. I'm not going to talk about all those here because it turns out we're going to restrict our antenna comments to antennas that are, used in the VHF and above regions of the frequency spectrum. Within these categories are numerous variations upon the general theme. So, what are antenna characteristics? Well, wireless antennas have several universal characteristics, including the following: radiation pattern, directivity, efficiency, gain, polarization, input impedance, bandwidth, and beam width. From a practical point of view, an antenna will be designed to have a standard input impedance for RF of 50 ohms. We will drive it with a 50 ohm coaxial cable probably. So what tends to be the most important is an antenna's gain. Furthermore, the gain of an antenna usually determines its beam width. They are inversely related. Again, we'll talk about antennas for VHF and above, which is B 300 megahertz and up. The systems used for wireless networking all use VHF frequencies and above, so we'll focus on antennas for these frequencies. As soon as we get into the higher frequency ranges, with shorter wavelengths and therefore smaller antennas, we bring in the concept of array antennas. An array antenna allows one to make a highly directional, i.e. narrow beam antenna structure, and taking that one step further, a steerable or beam-forming array antenna. An antenna that's beam of radiated energy may be pointed electronically. And again, it's reciprocal, so if we wanted to receive a signal, we could receive from a particular direction. So let's look at the popular Yagi-Yagi antenna to get an idea of how these directional array antennas work. Typically, one starts with a half-wave dipole antenna as a basic array element, and then adds more of these parts or slightly modified elements, that is, the length or spacing might change, to shape the radiation pattern to a narrow beam of energy. Now, we refer to the half-wave dipole element as a driven element when the antenna is used for transmitting and is connected directly to the system transmission line. So here's a nice picture of a stacked Yagi array. So this picture shows a pair of stacked Yagi antennas for use at about 900 megahertz. You can see the coaxial cable is connected to the driven elements of each of the antennas. So there's a coaxial cable that comes up, and there's a T, and each side of the T goes into one of the antennas. Now, it looks like it goes into the end of the antenna, but you might notice there's one element. It's the second one in from the left, and it has a little protruding piece of metal that comes out and attaches to the element. So actually what that is the center of the coaxial cable is insulated from the rest of the antenna, and it attaches at that point on the driven element. There's a term for that type of attachment, but we won't go into that here. The four shorter elements to the right of the driven element are known as directors and narrow the beam. The one longer element to the left of the driven element is known as a reflector, and does just that, reflecting the radiated electromagnetic wave to the right. And the other thing is stacking two antennas yields twice the gain. So here's a couple pictures of Yagi radiation patterns. One is in the vertical plane, the other is in the horizontal plane. So these diagrams indicate the typical radiation patterns for a high-gain Yagi antenna. The patterns differ a little bit relative to one's orientation to the elements, that is either vertical or horizontal. These are known as pencil beam patterns, like those produced by flashlights, and are used for point-to-point applications. You might notice that there's that main lobe or beam. Then there's a bunch of what we call those side lobes off of the center there, and again, that has to do with the practical aspect of these antennas. Reflecting surface antennas are our next topic. So another very popular high-gain antenna for microwave frequencies is the parabolic dish antenna. This is the antenna one sees on people's homes or apartment buildings for receiving satellite TV. For this particular antenna, a reflecting surface focuses the electromagnetic energy on a half-wave dipole antenna at the focal point. This is the type of antenna that is needed for satellite-based internet access, by the way. So here's this nice picture of a dish, high-definition satellite dish, parabolic dish antenna. So this modified parabolic dish antenna uses a reflecting surface to focus the electromagnetic energy that it intercepts onto 3 different receiver modules for the signals transmitted from 3 different satellites in high geosynchronous Earth orbit. So you can see in the picture 2 of the focal points. There's another one over that's, blocked by the structure there. The size of this thing is about 20 inches across the dish. The solid reflecting surface, or the reflecting surface, doesn't need to be solid, could be a screen. You might recall the discussion of the front door window of a microwave oven and its reflection properties. Satellite TV typically uses a Ka band or slightly under 20 gigahertz frequencies. This antenna would typically have a very high gain, for instance in the thousands for this particular frequency range. Next antenna we'll talk about are microstrip patch antennas. So the antennas discussed so far have their most usefulness in applications involving narrow beam point-to-point transmission. Let's consider a cell phone. For use in cell phones and other mobile computing devices, microstrip patch antennas are preferred where small size and lack of a need for any special orientation of the device are the most important antenna design characteristics. These antennas are usually flat and can be adapted to a device's shape. That's known as conformal antennas. So here's a picture. This is a 16 patch microstrip patch antenna. Photo shows a 4x4 or 16 element microstrip patch antenna, array antenna rather. Each patch is equivalent to our half wave, that's our wire-based dipole antenna discussed previously. The patches are fed by specially designed transmission lines that, like the patches, are on the surface of a printed circuit board, a PCB. The PCB consists of a thin piece of dielectric material on top of a ground plane, which is a copper sheet, with copper patches on the dielectric material. And you can see those copper patches to the left in that picture. This pattern gives the array antenna maximum gain perpendicular to the surface of the printed circuit board. So that would be coming out at you from the slide. Here's 2 more pictures of microstrip patch antennas. The photo on the left shows a 2-element microstrip array and shows its flexibility. We tend to call it flexible electronics. The other one shows the person bending the actual microstrip antennas. Very flexible. And again, that term conformal. So today we have reconfigurable antennas and arrays. And the next big advancement in antenna technology, which is almost out of the lab, will be reconfigurable antennas and arrays for mobile devices. These types of antennas will be realized using microstrip technology or IC antenna technology, that is antenna elements on the chip, for millimeter and sub-millimeter wavelength applications. They will have the ability to alter their directional patterns, we call that beamforming, and their frequency of operation for use on multiple frequency bands. So let's talk about some practical considerations of antennas. We have talked about how electromagnetic wave propagation effects can alter the received signal strength of a wireless system, but what about the idiosyncrasies of antennas? Well, when locating a wireless networking device, it should be noted that any nearby metal will affect the antenna's characteristics and therefore system performance. Certainly, locating the device inside a metal filing cabinet or on a metal bookshelf case will most likely degrade performance greatly or at least change it. What happens when a non-conducting material is nearby an antenna? It depends upon several factors such as the proximity, the loss characteristics of the material, and the wavelength or frequency of the signal applied to the antenna, which relates to the antenna size. Paper or books would not have much effect on the antenna, but hiding a wireless LAN access point behind several flower pots or letting the family cat sleep next to the device would degrade operations somewhat. The cat's body would absorb some of the signals power, but don't worry, it would not harm the cat. These unfavorable effects will become more pronounced as wireless LANs utilize frequencies in the millimeter wave regime. Even one's hand would have a noticeable effect on signal strength if placed near or in the proximity of a millimeter wave wavelength antenna. When locating these types of wireless access points, care will need to be taken to keep them away from metal objects or any other objects that could affect their operation negatively. So let's summarize antenna theory. Advancements in antenna technology, things like MIMO, multiple input, multiple output antennas, have already had an impact on wireless data transfer rates, with the present speeds exceeding 1 gigabit per second for wireless LANs. The use of millimeter wave bands will allow and require creative designs for LAN-based technology through the use of advanced antenna technology, techniques like antenna beam forming, and so on. The antennas for these new wireless networking devices will play a much larger role than they have for prior generation devices. And that's it for this presentation.